Hi class, so we meet again in this video. I'm going to show you an example on how to solve for the Otto cycle problem. So let's have a look at this question here. We have a compression ratio of an air standard Otto cycle is 9.5. Prior to the isentropic compression process, the air is at 100 kilopascal, 35 degrees C and 600 centimeter cube. The temperature at the end of the isentropic expansion process is said to be at 100 Kelvin, and using specific heat values at room temperature, we need to determine the highest temperature and pressure in the cycle, the amount of heat transfer in kilojoule and the thermal efficiency, and finally the mean effective pressure. Alright, so since we are solving for this Otto cycle, so let's plot the PV diagram first. Okay, so you have a PV diagram. Sorry. This is your volume and this is your pressure. And for Otto cycle, you recall back in the video, so we have a bottom dead center and there's another one, your top dead center. And you connect this one and also this point here. So the process starts with the compression at state 1 until it reached your top dead center, which is state 2. And in Otto cycle, right, your heat addition or your combustion process happening at constant volume, and then it goes to state 3 where the complete combustion process is happening, and then your piston cylinder are going to expand, and finally it will reject your product of combustion as an exhaust gas. So we define this for one state as Q out, right? So given to you your compression ratio, or you can have a RV instead, right, which is V max over your V min, or in other words, in this case, your maximum volume is at 1 and your minimum volume is at your top dead center. So it is actually equal to V1 over your V2, and it is equal also to your V4 over your V3, and it is given to you 9.5. And there's others property were given to you, which is at state 1 your P1 is 100 kilopascal, and that your temperature 1 is 35 degrees C. This one you need to change into your Kelvin, and also you were given the volume where your V1 is actually 600 centimeter cube, or if we change into meter, it's going to be 0.6 meter cube. And you were also given the temperature at the end of the isentropic expansion process is 800 Kelvin. So this is where your piston is expanding, right? And this process is your isentropic expansion process. So it says at the end of the expansion process, the temperature is 800 Kelvin. So basically, this 800 Kelvin is the temperature of your T4, right? Your T4 right here. So your T4 is equal to 800 Kelvin. Now, what is the thing that you need to find? You need to find the highest temperature and pressure in the cycle. So as I said in your previous class, the highest temperature and pressure of the cycle must be at state 3, where your fuel and your air is fully combusted. So it will gives you the highest pressure and temperature, right? as you can see in this plot here. And also you need to find the amount of heat transfer in, which is you need to find your Q in. So you will need your temperature at 2 and temperature at 3, and also the thermal efficiency. So let's solve this according to state by state first. So we will solve this according to state by state, right? So from state 1 to state 2, the process is actually isentropic compression. So therefore, because of this isentropic compression, therefore you can make use of this T2 over T1, V1 over V2, K minus 1. This one you need to recheck from your notes given to you, right? So in this case, we already, if you have a look at here, this is actually your compression ratio over here, and it's already given to you 9.5. And according to the question, you may use constant specific heats. So we take the K for your air as to be 1.4. So T2 here is equal to your T1, which is 308 Kelvin, times with your compression ratio, which is 9.5, taking K as equal to 1.4. So now it is 0.4. And finally, you will get your temperature at 2 to be, so your temperature is about 757.95 Kelvin. Next is to solve for your state 3, okay, which is if you go state by state, state 2 to state 3 is actually heat addition at constant volume, right? So since it is at constant volume, so your V3 must be equal to your V2, and we make use of this PVMRT. So PV is equal to MRT. So if you place your hands at V, right? You cover your hands at V, so it will be MRT3 over your P3 is equal to MRT2 over your P2. So given that this problem is about constant volume, constant mass, so mass you will be the same, and we will use R air, so it's going to be constant also, so you can cancel out. So left with you your T3 is equal to your P3 over your P2 times your T2, right? So how will you solve for your T3? You will need the value of your pressure at 3 and also pressure at 2. So we leave at that first, and then we try to go for the next process, which is isentropic expansion between state 3 and 4. Now let's solve for your state 3 to 4, which is this is an isentropic expansion. So you are going to have your T3 over T4 is equal to your V4 over V3, and it is K minus 1. So your T3 now is equal to your T4 times with your RV 0.4, which T4 is already given to you 800 Kelvin, right? Your T4 is already given to you as 800 Kelvin. So you solve for your T3 is equal to 1968.69 Kelvin, where this remarked as the highest temperature in the cycle. Okay. As the question asks you to solve for the highest state 3, the value for the temperature and pressure. So next we are going to look for the pressure, and using these isentropic relations. So now you got to find your pressure here, right? This is only valid for ideal gas, and it must be isentropic process, and the specific heat must be constant, right? So you can make use of this temperature pressure relations, or also you can make use of this pressure and compression ratio relations, right? So this one is denoted as 2 and 1, and the compression ratio is between V1 and V2. So in this case, we are trying to solve for 3 and 4, so you can make use of compression ratio between V4 and V3, just as the same with your temperature over here. So let's say we make use of this P pressure and compression ratio relations, so that you will get the pressure at 3. So we make use of this pressure and compression ratio relations. You bring this power to your right hand side, so it's going to left with you K. So now you need to find your P3, therefore you will need your P4, but P4 is not given here, so we need again to proceed with the next process, right? So that hoping that we are going to find the value that we need in 4 with these relations at 1. So we continue with state 4 and 1. State 4 and 1 is a process of heat rejection at constant volume. So we make use of this PVMRT to look for your pressure at 4. So you can substitute in this previous state to solve these two things that we haven't solved yet, right? So we make use of these PVMRT relations again, and between 4 and 1. So volume at 4 is equal to volume at 1. So you close the V, you bring your P to the right hand side, so it's going to be MRT4 over your P4 is equal to MRT1 over your P1. And again, this is a constant mass and your specific heat is constant, so you can cancel both M and R terms. Now that you are trying to look for your P4, so we arrange it to be, so we already have the T4, which is 800, and the T1, which is 308 Kelvin, and as well your pressure one, which is 100 kilopascal. So it makes your P4 is equal to, now that we already have the value of P4, so we can substitute into these equations and then try to solve all the temperature at all states that we need. Alright. Now you substitute your P4 value into these equations and times with your compression ratio, and finally you will get 6072.28 kilopascal. So as you can see in this PV diagram cycle, this makes the highest pressure over here. Right? So now that we already list all the temperature that we need, and we have solved for this pressure and temperature previously. So next we are going to find your work net, which is Q in minus your Q out. So you substitute all the values that you need into this equation, and because this is constant specific heat case, so your CV air is equal to 0.718. So finally you will get your work net is equal to this value. Next is to find the thermocycle efficiency. You can make use of these equations, or when you expand it become like this, or when you simplify it become like this, and then times with your 100, so you are going to have this much value of your thermocycle efficiency. In solving for your MEP, which is mean effective pressure, right? This is actually the derivations of work is equal to pressure times if the change of your volume. So when you rearrange these pressures, it's going to give you W over volume, or work net over the change of this volume between bottom dead center and your top dead center over here. You can make use of this equation, or you can have this one, which is already simplified into this compression ratio. Therefore, you will only need to find for your V1. If you are using this equation, so you need to find your V1 and your V2. This V1 and V2 can be obtained from these equations, right? Even though the mass is not given, you can always use specific volume value. But in this example, your V1 is already given as in centimeter cube, so we change it into meter cube. So it's going to give you 0.0006 meter cube, right? So there's no problem if you using directly this equation. So you already have been given your V1, your RV is already been given, and you already found your work net here. So you just substitute all the value into these equations. However, there's another option, which is you can make use of this one, right? If you if you didn't memorize this, you can make use of this one, but yet you need to find your V2 over here. So you can find your V2 by using the compression ratio relations, right? So as you know, the compression ratio is between V1 over your V2. So given to you, V1 is equal to 0.006, right? So you will going to have your V2. So once we obtain the value of V2, we make use of these equations. So you are going to have this value for your MEP. Or you can make use of these equations. It's going to give you about the same answers here. So what about this example is already given to you V1. So what about if V1 is not given? So you can make use of this PVMRT here to find your V1. And even if the mass is not given, you can still make use of specific volume to find your specific volume at 1, and then you can substitute in these equations or in these equations, right? So we have already done with this Otto cycle that using your petrol or gasoline vehicle. Next we are going to try on your diesel cycle. Thank you.